So feel free to raise your hands and ask out questions. I always tell that before any of my sessions. And let me tell you this session is more for you guys than for me, because I will change the way the session goes depending on the crowd feedback. Okay, so it's not necessary. Like I do have slides. We'll go through the deck, but going through the whole slide deck is not my motto. It's not my motive. Sorry. We will have that available on the internet for you guys to go through the presentation, but I like to have much more of an interactive audience. Before I start, that was one. The second one is I want you guys to give a round of applause to all of the Salt March folks out here, because they have done a phenomenal job. And trust me, since this morning, we have been struggling with the Wi-Fi connection, and I had like about 5 people enveloping me trying to get my stuff working, and it's just awesome. So kudos to you guys. And if the demo works, it was because of them. If it doesn't work, because I messed up. Okay. So to introduce myself, I think he did a good job, but to give a brief background, I'm based out of Salt Lake City, and I'm not a computer science major. I'm a mechanical engineer, and I did my bachelor's in mechanical engineering from MIT Pune, so Pune University. Then went in 2010 to University of Utah in Salt Lake City. Did my master's out there in mechanical engineering again. Did a specialization in robotics and controls, and that's where we used to build out bigger things. But then when I ended up joining Goldman Sachs back in 2012, when I joined, I had not written a single line of Java code in my life before that. But my team and everyone pretty much sat with me, like mentored me. They took me through the whole SDLC process. Like they got me up to speed, and now I'm pretty much trying to pay it forward and trying to get these small workshops and everything in place so that many more people can enjoy the art of coding. Okay, and I love to conduct workshop for kids, because I think the whole STEM, science, technology, engineering, math, until and unless it's inculcated from early on, we are not going to get like people who are going to be interested in writing code or engineering or anything like that till we get them motivated. So once you target it at the grassroots level, then it sort of helps. So you can see it's an elevator out there. It's sort of the most simplest thing, and it's kind of my canary test out there for people who we ride a lift every day, right? Lift, elevator, but not many people know how it works, and you really don't need to know how it works. But when you're trying to teach something related to robotics to kids, then you want to make sure that it's something close to what they use on a daily basis. So that's why I came up with this elevator workshop. The first time I did was on the island of Crete in Greece, and there are people who don't even have a laptop, who are not used to computer programming and all of those things. They got to come and build out these things. And I think Steve Chin, whose equipment I always borrow, he'll end up stopping by later on. But if he doesn't, like he always lends me out his kits, and it's phenomenal, because all of us are sort of like a big consortium who likes to organize these workshops for kids. And here you can see that was my very first Lego Mindstorm. So today we are going to deal with Lego Mindstorms, and I'll take you guys through what exactly they are. But that was my very first one, and it was at Java 1. How many of you have heard of Java 1? Okay, so the very first time I went to Java 1 a couple of years ago, one of my mentors from Goldman Sachs actually gave me a challenge. He was like, yeah, you're a robotics engineer. And I was sort of telling him like, yeah, how I'm interested in robotics and I want to do something. And he's like, how about I buy you a Mindstorm? Because like they're fairly expensive. They're not cheap. Like, how about I buy you a Mindstorm? And if you can pull off like making it work with Java, do all of these things, have a demo set up, and we demo it at Java 1, I'll pay for that. So that was a nice motivation for me. And from there on, that was my second one, where it's a fire truck, and we're going to see a video about Towers of Hanoi. It can solve Towers of Hanoi. That's pretty much the first video we'll see. These two guys are out here. We are going to end up demoing towards the end of the session. And then that's the elevator. I'm going to live code it. Okay. Let me just turn it on. So, what are we going to do today? First, we're going to see a robot video. Why? Because instead of putting out some charts and graphs, I thought, let's have a robot video with a logical problem being solved in physical aspect. Then, we are going to go through what is a mindstorm and how you can program it and how you can actually, even as adults or as kids, we can end up having fun. Then, we're going to sort of step it up a bit. We are going to do some motion planning algorithms and see what all things you have to do to make it work in a smaller system. Because these days, just scaling up is not a problem, because that has been done over and over again. But scaling down, that's a whole beast in its own domain, right? So this is sort of a problem of scaling down. Like, I have this very small microprocessor. It has 64 MB of RAM. It is a 500 megahertz processor. And then I have to actually determine the path using a Dijkstra or an A-star algorithm. And then, if time permits, we'll go through JRE versus compact profiles. I'm not that motivated to cover that, but there are like enough demos out here, so I want you guys to have fun, okay? So, feel free to interrupt, ask questions. I'm more than willing to take time to answer. Okay, so the very first one. So how many of you know what is Towers of Hanoi? Okay, can anyone explain what is Towers of Hanoi?
So there will be 3 towers and we have plates of different sizes.
Mm-hmm. Yeah. Yep. So it's I'm going to add more to it. So and you guys can keep on seeing the video while I illustrate what the problem is. So it's one of the most fundamental logical problems that computer scientists get to solve, or robotics engineers more so. So you have 3 rings, okay? These they call rings, and this is in my living room at my house. So these are 3 rings, and assume that they are of decreasing size. Okay, so the biggest one is at the bottom, which is the base, then it's the middle one, and then there's the smallest one, which is at the top. You want to assume that there are 3 pegs, okay? You want to go from the 3rd peg to the 1st peg where you can only lift 1 ring at a time, okay? Also, you should never ever break the order. That is, the smaller ring should always be on the bigger ring. It cannot be the other way around. So the way it ends up solving is you have to get the smallest one, go to the 1st peg, put it, then you go to get the middle one, go to the 2nd peg, put it. You have to go back to the 1st peg, you can see, then put it in the middle one, and then go fetch the largest one and put it up front. Now this is a fire truck which you guys saw before. All right, and that is seen to solve the Towers of Hanoi. This was something which I created using Legos. So the towers, the fire truck is a stock kit which you can buy in a Lego store. And then on top of that, there is this electromagnet which I created, where when it detects the disk, it stops. It moves it down. Then it triggers the electromagnet. It magnetizes it, picks up the ring, goes up, and puts it down. All right. So these are the sort of problems that you want to solve. I mean, these are easy enough when you're solving it on paper or when you're writing code for it, but they start getting slightly difficult when you're dealing with a real-life physical system. Okay. So I think all of you guys get the concept. I can wait for the video to finish, or else we can move on to the next one. I guess it's just 10 seconds, but yeah, that's it. So it ended up solving the whole Towers of Hanoi out there. Okay. And then again, one of the things, it has to come back to its own original position. So that's one of the things. All right. So going back here, any questions so far? Why did we even look at Towers of Hanoi? Okay. So the next one, it's Java versus EV3 programming app. Like I mentioned a couple of times before, this is the Lego Mindstorms. It's something which you get off the shelf. What you get with it is 2 pilot motors, 1 servo motor, a few sensors. And you get a microprocessor, which is the configuration which I mentioned before, that you can program to do whatever you want. With the with the Mindstorms kit, you actually, it's something which is available on the internet, available at the Lego site. You can go and download it. And basically, it's a nice visual and programming interface. And what you do is you basically drag and drop every system, like a motor or a pilot or a sensor, and then you program it. It is designed for kids to use. Okay, it's something which is like the very first step that you take to see, hey, does the robot twitch? Does it go forward and backward? All right, that's something which you do. But then, and again, it's available at the Mindstorm site. I'll be pushing these slides out on the web, and then you guys can download, and all these links are, those are all hyperlinks. You can just go see more. But that's not enough, right? Because one of the most it's fine for little kids. It's fine for us to just use those drag and drop programs. But when you want to step up the game and solve some complex algorithms, it's not enough. You need basic things like storing a variable, creating a loop, breaking out of a loop. I mean, all of those things are available in the, except for storing the variable, but all of the other things are available in the app, but it's not as programmer friendly. All of us are developers, I hope so, right? All of us write code, and if someone is sitting and describing us as a complex problem and like, oh, this is the reason why it's not working, blah, blah, you'll be like, okay, just show me the code. Like, I'll be able to talk better in terms of code than you explaining this whole block diagram, right? It's pretty much that thing. So LeHos, it's an open source software, and it's basic. When I say a software, it's something which they have done in extension. And again, this is a whole community which is not attributed to Legos, but I think, I don't know what is their motivation, but they created this awesome standard JRE. And all of those Mindstorms are basically ARM devices. So on the Oracle website, you can always download the standard JRE for an ARM processor. Once you get that standard JRE for an ARM processor, you have to bootstrap it with the LeHos, the LeHos JVM, the standard library, so that you get all the APIs for the servo motors, the sensors, and the callbacks, etc., etc. All right, and what this enables you to do is you can open up your favorite IDE like Eclipse, IntelliJ, NetBeans, whatever you guys like, and you can just write code which is just Java code. You can have streams on it. You can have other collections on it. You can basically, even if you want to, like today we are going to integrate these two robots with the Twitter API. Normally people tell you to not use your phones in a talk. I'm going to ask you to please use your phones and tweet commands to them. And I'm going to show you which commands, and then these guys. So all of these things, these are sort of higher level of abstract. Like these are like the higher programming problems, right? And that's something which you cannot actually solve with the standard available software, standard available Lego software. Also, it's phenomenal for precise motor control, and that was necessary for the Towers of Hanoi. That was one of the reasons why I showed the very first video, because you could see you have to stop where the disk is, right? You cannot end up like going haywire somewhere else, because otherwise if you don't stop where the disk is, then the crane does not pull down the electromagnet properly. Then you cannot lift it up properly, right? So like I said, LeHos is a standard JVM. So you write code similar to just Java code. And if you want to, another advantage of Java is the amount of third-party open source libraries which are there. I mean, I don't think anyone can contradict me on that. Like, there is just so many things out there which many people have just taken care for us. Like, if it is a collections library, if you want to do certain sort of collection, we're going to see how I've used those collections in the next talk, in the next few slides, sorry. And then you can even put up your own database and access it remotely, all of those things, right? So with this being a standard JVM, all you got to do is put it on your class path, and then it works. It's exactly similar to another Java project. Okay, now I stop here for a live programming demo, and here we are going to program the elevator. Like I said, the first time this was done was at JCrete for Kids, sorry, and it's one of the most simplest things. You get those Lego kits, you end up connecting them, and you can see for the belt, I'm actually using a thread which I got in my hotel room, right? It's not like, I don't need to have like a very high fondue like a belt and pulley system. Okay, and with I have this code written out, and I'm going to end up deleting that, and we'll end up starting from scratch. But one of the most important things is you can see that I'm going to use Eclipse, and it's me writing code like you guys. So if I struggle, you guys got to help me out, okay? And it's the standard API. So first, let's go delete this. All right, now I know for a fact that this is one motor, which is an NXT regulated motor. It's in port A. If anyone wants to come see, you're welcome to come and see. And then I have the IP address of my Mindstorm, and it's just connected via USB. What I do is I basically need to first get my NXT regulated motor, right? And I'm just going to call it motor, okay? And then I need to make sure that, hey, I have to tell Lihos which exactly motor, which port is this motor on. I said before it's port A, so you can do motor.a. All right. Oh. So once you have motor.a, now what is the lift supposed to do? Go up and down, right? When it is down, it's supposed to go up. When it is up, it's going to go down. We're not going to write that much of a complicated program. But what we are going to say is, hey, if you press the up button, go up. If you press the down button, go down. Now, right before you guys walked in, I ended up putting that belt on. So it is possible that when I say up, it's actually going to go down. And if that's the case, we just have to flip the direction, right? So I'm going to create a Boolean out here to say you always need a override. So, and while I'm running, again, using the Legos API, the Lihos API, you actually get all the access to all the ports and all the buttons. So you can say that, hey, just wait for any key press, okay? So you got to wait for or you can wait for an event. It's up to you. It doesn't matter actually. And then you're going to store the button, the ID of the button, because each button has an ID: up, down, left, right, enter. Okay. And then depending on the ID of the button, you're going to decide what to do. Okay. So if button equal to button.up.getID, okay? It's as simple as that. It's you writing. Again, this is the power of using a third-party library, because you have pretty much delegated the entire problem of interfacing this to them, okay? You're not worried about it right now. So if it is up, what do I want to do? I want the motor to go up, okay? So make the motor rotate, okay, for an angle of, I'm going to put, let's say, 720 degrees or 900 degrees. We'll say 900 degrees. And the reason why I know it's 900 is because I've done this before. All right. So with this 900, and then, now what if you press the down button? You want to do that. So again, motor, then this is minus 900. Now we'll see whether it goes up or down. And then always, the most important thing is in a software, in a whole program is how to exit. Because if you do not know how to exit, then this is going to go on forever, right? So you want to say that, hey, if I press the button, which is equal to button dot, let's say the enter key or escape key, anyone. I pick the enter key, okay? Then just make run equal to false. All right, simple enough. And then as good citizens, you want to do a system dot exit 0, okay, because everything is fine. Now you can see there is a reason why I'm using Eclipse, and you could see me struggle typing in Eclipse because I'm more of an IntelliJ IDEA user. Okay, it's my personal preference, and I'm just used to the keyboard shortcuts and everything. But Eclipse has an inbuilt plugin for Lihos, so I apologize for the resolution, but with this plugin, you actually get a control center like that. Okay, when you guys pull it up on your own laptops, it will look better. Again, I apologize for that. And then you can search for the brick, and it should show up out here. Now I can see there are 2 bricks because I've connected 2 things out here for my next demo. But I'm going to use that one, and that one's IP address is 3.1. So once I connect, all right, so I've finished connecting it. Now all I got to do is right click and run as a Lihos EV3 program. What this does is this will end up creating a jar of my program. Then it will end up pushing it out. It SSHs through and it goes here. And for the folks who are sitting up front, you could have seen that there is a Duke. You guys know Duke, like Java symbol. Like it was saying, wait a second, okay? And now it's actually waiting for my command. So let's see if so yeah. When I press the up button, it goes up. When I press the down button, it goes down. Now again, you guys must be thinking, oh, what is so unusual in this? This is the most straightforward thing. It just goes up and down. What is so special? But think about it from a 10-year-old's perspective, right? They actually build this out and they program it. Like they write that code and then they see go up and down. It's a sense of achievement, trust me. And you can keep on going up and down as much as you want and then press the center key and then it will exit itself. Okay, so that was my very first programming demo. Any questions in this? All right. Switching back to presentation. Okay, now that you saw how the towers of Hanoi worked, you saw how the simplistic program worked. Now we are going to sort of up the stake a bit, and we are going to work on Dijkstra and A*. Okay, before I go to Dijkstra's, who knows what the Dijkstra's algorithm is? Anyone else? Yes. So more than the shortest path. No, that's not Dijkstra's algorithm. Exactly. It's the minimum cost path. So Dijkstra's algorithm is where you want to find a path between your start point and the end point, and the cost has to be the least. Okay, so the minimizing function in pure math is the cost. As long as your cost is minimum, the least, then that's the path which is desired. Now you can figure out the cost however you want. I mean, like let's say in x direction it's 1 unit, in negative x it's 1 unit, in positive y it's 1 unit, in negative y it's minus 1 unit because it's cheaper to go down. Just for an example, okay? So another salient point of Dijkstra is a knowledge-based algorithm. What that means is you need to know the whole maze or the whole, not just the maze, so to say like your whole domain beforehand, okay? And then the traversal between each node has a fixed cost to it, Okay, so if you're going to go from point 1 to point 2, then that has a cost to it, and you need to know that cost beforehand, as well as you need to know which all nodes can you connect to, and you will see what I mean by that. And it was conceived by Professor Dijkstra. I really cannot pronounce his first name, I'm sorry. So this is a small Wikipedia GIF where you got to go from point A to point B. And you can see that each of these nodes have connection matrix. And each of the connections has a cost associated to it. Now once you go from point A to point B, the final path that you will get, that will be the least cost path. Okay, you guys see what I'm saying? And then you will see it keeps on bringing out stuff, yeah. So 20 of 4 is greater than or equal to 20 of 5. So that means your minimizing function has been satisfied, and it is going to go ahead and choose that path. Okay, any questions on Dijkstra? Then an extension to Dijkstra is called the A-star algorithm. Actually, the way it came into evolution was there was an A1, there was an A2, there was ... finally AN. So someone said that, hey, we just cannot keep on doing this over and over again. We are just going to call it A-star. And then what the extension basically is right now Dijkstra is a plain old least cost path, right? That means going from point A to point B, the cost has to be the least. But there is no way that you can actually end up directing your path towards your output, right? Like the best example, let's say you're going to go from Pune to Mumbai, okay? You have two options. Once you take the expressway, the other one you take the old Ghat route, all right? Now, I do not know which one is shorter and which one is lesser cost, but for the purpose of this, this experiment, we'll call the old one has the least cost, okay? But that is more time consuming, right? That way you're not satisfying anything. But let's say you want to add a heuristic to it. You want to say that, hey, I'm fine that you keep on looking at the least cost, but the more important thing is I want you to sort of direct me towards the target. I want you to, let's say, make it the shortest path or make it the most ecological path. If you ever use like your GPS, then on there you would see like there are generally 3 options, right? The first option is the shortest path, the second one is the most ecological path, then there's the fastest path, right? So it's not necessary the ecological path is the shortest path. It's not necessary the shortest path is actually the fastest path, because you have speed limits, you have multiple other things, you have traffic jams, right? So it's up to you. And in order for us to actually achieve that, what you do is you update the minimizing function to add the cost plus a heuristic. And like finding the heuristic is actually an art more than a science, and it varies. Your mileage may vary, it depends. And you'll see how the heuristic affects the path. So just to recap, your Dijkstra, the minimizing function is f of n is c of n, so cost of traversal. A star is f of n is c of n plus h of n, where h is the heuristic. Okay, you guys with me so far? Yeah. Now, the next one, actually running the Dijkstra's or the A star algorithm on EV3. Now, how many of you think that the Dijkstra's algorithm is trivial? That's pretty much the third thing that anyone does in motion planning. The first one is BDS and DFS, and then the third one is Dijkstra's. How many think that it's trivial? It's actually pretty trivial, but it's very difficult to implement. And it's even more difficult to implement on a physical system. And you'll see why. So our problem statement here is there is a maze. So imagine and you will see the maze in the next slide. So imagine there's a maze. What is a maze? You go from the start to the end, and there are obstacles in between which you cannot pass, right? Then I'm going to say that the motion in x direction costs 1x of the absolute distance. Now I had to give some cost to it, right? So that I can actually use Dijkstra's on it. So again, this is an arbitrary cost. Okay, and also I'm going to say that the motion in y direction costs 2y of the absolute distance. Okay. This was my maze. Okay, this is the start point, and this is the checkered flag is the end point. Okay. Now you can see there are 2 options of the path. One, you can go here, The other one you can go here, okay? Now you would see there are many, like if at a glance, this seems to be the most least cost path, correct? This seems to be more expensive. And you will see how the A star heuristic affects which direction it chooses it, okay? So the very first thing that you have to do with an A star algorithm is, or a Dijkstra's algorithm is, like, since it's a knowledge-based algorithm, you have to make sure that your entire graph is captured. And when I say your entire graph is captured, you have to make sure that each of these points is accounted for. And you can actually compute whether you can traverse that direction or you cannot, okay? Any questions so far? And then what I do, again, the only reason why normally people say that, hey, red is actually danger, blue is all right. But you would say, I flip that around. Red is passable, it's traversable, whereas blue is an obstacle. And the reason why I did it was for the presentation purpose. Otherwise, if the whole screen was blue, you guys would be like ducking for cover. You'll be like, we can't see, okay. What you can do is you can form an adjacency matrix of the whole x and y coordinates. And when I say adjacency matrix, what that means is point 1 is next to, let's say, point 0, 0 is next to point 1, 0 and 0, 1. Okay. Then point 1, 0 is next to 0, 0 and 2, 0, as well as it is next to which one? 1, 2. No, 1, 1, sorry. Right? It's basically that matrix that you can end up finding out, that you can end up forming. And then once you have the adjacency matrix and the color data, you can actually find the successors. Can I go from this point to the other point? Okay. So, like you saw before, the graph which was there, I need to store that on my system, which is that small microprocessor, right? How many of you guys work in Java out here? Okay. Are collections objects? So can you store primitives in a collection, or you can only store objects? So you can only store objects, right? And how much memory does an object take? Well, that's true, but on an average, let's say it's an int. So int versus integer. An integer takes how much? And how much does an int take?
Int takes 4, integer takes 12 plus around 8 bytes.
Exactly.
So 12 bytes over.
So it takes 12 bytes versus 4 bytes, right? So you're increasing the memory consumption by 3 times. And again, this is a scale down problem. Like I don't have a 1 gig JVM where I can basically just box and unbox, right? So that's why I had to use primitive collections. And you can see it's mutable object int map. Now you'll be saying, okay, what is this map? So I'm a project lead of Eclipse Collections, and Eclipse Collections is an open source collection framework which Goldman Sachs first open sourced in 2012. It was called GS Collections. We migrated it to the Eclipse Foundation in 2015, I believe, and at the end of 2015, and we rechristened it to be called as Eclipse Collections. And we have our own primitive map set list. And if you guys attend my talk this afternoon called as Collections Compare, that's where I end up comparing multiple collections. And that's much more of a technical topic than this being more of an interactive / a fun topic. And there you can see how actually the memory and the performance is impacted by these collections frameworks. So again, going back to this, this presentation, so I have a mutable object int map. And the reason why I have that is because my coordinates which are there, I can just number them, okay? And I can just create an object called as point, all right? And then the RGB data which is there, I know for a fact if something is red, that means it's not brown. So I can choose to store whatever I want. So here, I say that my red is 256 and my blue is 1, okay? Now that's an int. So I'm going to keep it at 4 bytes, okay, instead of keeping an integer. Now, does it work with an integer? Does it work with the hash map? Yes, it does. I've tried it. It works fine, okay? But it is not you want a system which you can rerun over and over again, right? And with this small processor, whenever you're having so much of memory churn on there, it is going to create what? GC overhead, right? And now if you're looking at an IoT system where, let's say, you deploy something in the Amazonian rainforest and you don't want to go see, like you don't have the liberty to go change the batteries every month, right? I mean, you really cannot. You want to deploy that thing and you want to come after, let's say, 10 years or something like that, right? Because again, every time you're going to do processing, GC is processing, there is overhead on it. You're going to create heat, you're going to create power drain, right? So again, that's one of the reasons why you ended up using that. Again, you can do it with a hash map, but it cannot rerun. And I have tried it before, okay? So what I end up doing is I store my whole graph in an object int map with point being my key and the value being the the red or the blue value. Okay, if it is 1, it's blue, so it's impassable. If it is 256, it's red, it's passable. And what you can do is you can find the successors because of that. So again, a whole adjacency matrix means that you know your neighbors. And if you know your neighbors, you need to store each and every connection of those neighbors. Now, I'm working with a 64 MB JVM. Okay, again, scale down problem. I have to compute this at runtime. I cannot store this because let's say my whole graph is of 15,000 points, right? So I need to store the successors of all those 15,000 points. I need to store the data, the RGB values of all those 15,000 points. And then I have to pick that up and run the whole algorithm on it. And that is going to take some memory, right? It's just not possible. So that's why what you do is you find out a way that what can you actually compute at runtime? What do you need to deploy, which is the most minimal, which is going to make your software work fine in a scaled down system, all right? And again, I'm putting this out as an example, but this is something which you guys will have to do whenever you're working in an IoT-based system because, hey, you don't get the luxury of having infinite resources. You are working in like this small of a world, right? So going back to this thing, the way you can find your graph, the way you can find your successors is you basically say that get me the negative x if negative x is greater than 1 of mine. So my negative x is I do my coordinates minus x minus 1. My positive x is plus 1. Same thing for y's. And then you go and get what is the value, what is the RGB value. If the RGB value is greater than 1, then hey, it's red. I can actually go there. Okay, and then you add it to the list of successors. And we are going to see how we're going to use the list of successors in the next slide. And you actually end up doing the same thing for negative x, negative y, positive y. Okay, you guys with me so far? Are you guys having fun or like it's a really serious crowd? So it's not supposed to be a serious topic though. Okay, and then again, one of the most important things of Dijkstra or A star is the cost function. You need to get the cost for me to go from my position to my next position, to my next successor, right? And then the way you get it is like I mentioned before, the cost in the x direction is one times or 1 unit of the absolute distance. The cost in the y direction is twice the absolute distance. So you end up getting the cost, all right? Now this cost comes very handy because you have to find which node to visit next. If you look at the whole distribution of how the Dijkstra algorithm works, it is a knowledge-based algorithm. It has to go and find out which all nodes are viable. If a node is viable, it has to explore that. Okay? And since it has to explore that, it needs to first find out which node it should go to. Now, you would say that, hey, Nikhil, but yeah, you can just look at any successor. It doesn't matter. I agree. It really doesn't matter. But you want to be smart in your system because, hey, if you have the least cost successor already with you, then it basically helps your system later on because then you're eliminating stuff. You're not trying to add and you're not trying to reprocess. All right? So what you do is you end up getting, you'll see again, me being the project lead of Eclipse collections, I use Eclipse collections in pretty much everything. And again, that's the power of using LeHouse. You can just upload a third-party library and do whatever you want with it. So basically, what I do is I use this function called as min_by. This is an API which is available on all our interfaces. And you get the min using the cost, okay? And I have the vertex cost map, and I'm keeping that map up to date every time, because each time you go here, so what is the vertex cost map? You need to make sure to know that, hey, how much did it cost to go to that vertex, right? If you do not know that, you cannot find the least cost, okay? That's one of the things. Again, that has to be computed at runtime. So since it has to be computed at runtime, and if you have 15,000 points, you are going to have a map of those 15,000 keys, because those points need to have, hey, for someone to come here from this start point, what is the least cost? All right, and this map goes on inflating over and over again. And that's another reason why you cannot, you have to make sure you have the most minimum amount of data required on the machine, okay? So first what you do is you initialize it with integer.max value, okay? If it is max value, that means it has not been traversed, okay? And then what you do is you go on you go on evaluating each node one after the other. And then if I find a node which costs less than what I have in that map, then I just replace it. I say, okay, if you're going to go to node 315 and it's the least cost is to go from 260, I'm just pulling out these arbitrary numbers right now, and currently you have 205, replace 205 with 260, because right now for my path right now the least cost is to go from 260, okay? And then you end up finding the path which is available. Again, you will see that I'm using a mutable stack. So one of the reasons why I use Eclipse collection stack is because our stack is actually, okay, let me ask you this. What is a stack? As, let's say, a stack of papers or any collection? And last in, first out, right? So it basically, if you have a stack of papers, let's say newspapers, the very first one you pick up, throw it out, right? Last in, first out. But did you guys know that JDK stack is not last in, first out? It's actually first in, first out. They put out another collection called as deck, which it's deck, right? Which is last in, first out. Okay. But JDK stack is not last in, first out. However, Eclipse collection stack is last in, first out. And that helps me collapse the whole path. Because the way you find out the path is, now I have this least cost map with me, okay? So I know that to get to the end point, it's cheapest to come from this point, okay? Now to get till the endpoint -1, it's cheapest to get to endpoint -2, endpoint -3, that way dot 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 up to the start point, right? So now I'm dealing with the problem of just flattening the whole path. You guys see what I'm saying? And in order to have something like that happen, the best one is a stack, because you want the last in to be the first out. Because your last in now, you see, if you're going from start to end, okay, since it's start to end, you have already found the path, okay, but now you're at the end point, in your algorithm. You have to go back, you have to traverse back to the start. Once you have traversed back to the start, you can always put it in a list. I mean, you can get the size of the map, or you can make it more inefficient by first putting it in a list and then reversing the list or doing something like that. Okay, there's nothing stopping you. But we are trying to optimize the number of operations and the amount of garbage we are creating. So collections like, a stack or a deck help us in that by saying that, hey, start at the end, come till the start, and just reverse it. Now the way you end up achieving motion is you just go on popping it. And this is what it yields. This is the path which Dijkstra creates. Okay, this is the least cost path. And that's what we had an inclination beforehand, right? This is what we thought that the least cost path will be. Now I'm going to show you the A star one. A star is exactly same as Dijkstra. Okay? if you look at my heuristic, it is the x coordinate of the endpoint minus x of 0.2, so where I'm going to go, the node, then y of endpoint minus y of 0.2, so y of the y coordinate of the endpoint and y of where I'm going to go to. Okay, so that's pretty much the simplistic distance formula, okay, which we had. But now let's say I don't like the right side. I want my robot to go from the left side, because I know for a fact that, hey, even though this is least cost, but it's bad terrain, right? So I can adjust that by fixing my heuristic out here. Here what I'm saying is, hey, instead of checking on the y coordinate of 0.2, keep on checking the x coordinate of 0.2. I want you to sort of going in the positive x direction. Does that make sense? So that's how I've, like a simple change like this can impact your whole output. Okay? And that's the beauty of A star, because you have the power to decide whether, hey, you want to be on the ecological route, do you want to be on the shortest route, or do you want to be on the fastest route? Any questions so far? No. Yeah.
Here, like on the node locators, yeah, you're working on the trajectory part, so it will be like immutable.
Sorry, say that again, sorry.
On the node locators, like
Uh-huh.
you're working on trajectory,
Uh-huh.
it will be immutable, right?
So the whole graph is immutable. The graph is not going to change. But where you get to, like the whole object cost matrix, that is always going to be mutable, because you should have the ability. So let's say you go from, let's say you go from this point to this point, okay? But you're going from this point to this point as well. Now you need to figure out, depending on your cost function, which is cheaper to go to the left or to go to the right. So that is kept mutable.
That is being done by the east to the
Yeah,
algorithm.
yeah. Any other questions? Okay. So at the end, the A star path or the Dijkstra's path, which the ones which were equal with the distance formula, is actually comprised of 226 nodes. Okay, that means I know that this looks like I know that this looks a very simple path, or this looks a very simple path. Okay, yeah, this is just a straight line. But in order to traverse that straight line, you have to go through 226 nodes. Okay. Now, if you are not smart enough in the robotics world, what's going to happen is the robot is going to go for it's going to keep on pausing between those 225 points. That makes sense? You guys see what I'm saying? So since it's going to do that, you do not want to have that, right? You cannot have a robot which is going to go, stop, go, stop, go, stop 225 times. You need to have motion uninterrupted. So any ideas how you can make it move smoothly? So the best one is you need to predict the future. You need to know, you have to flatten the path. And when I say flatten the path is, you have to figure out during the motion, hey, do I have to change the heading? If I'm going to keep on going in the straight line, I don't have to do that. I don't have to stop at all. So I'm going to end up compressing that. I'm going to end up compressing that. Then I keep on checking, hey, I actually need to move to the right, or I need to turn to the left, okay? At that time, I decide, okay, I'm going to turn, and then again I'm going to use the exact same algorithm or the exact same strategy to figure out, do I have to flatten the path? Now since I'm flattening the path, what I need is, I need my next point and the next point. Okay, and you need the next point because, hey, if the next point is in the same heading, but the next point is going to be in a different heading, you should go and stop at the next point. Okay? And that way you end up getting motion uninterrupted. Any questions so far? This was pretty much the end of the slide deck, and we are going to move on to demos. If there are no questions, then okay, cool. Hopefully the Wi-Fi works. Hopefully the robots work, and hopefully all of you guys can see it. So what I'm going to do is, so I've got these two EV3s, okay, and they have these small pellets on there, small balls, and you get it with the EV3 kit itself. And then I'm going to give you commands which you can tweet to them, and then they'll follow. So you have commands like forward, backward, left, right, sound gong. Okay, the sound gong basically operates the gun and it shoots a pellet. So let's see if it works. Am I doing on time? 10 minutes, right? Okay. And these are the commands. So how many of you are on Twitter? So I hope you guys will start tweeting commands, which will be like, so this is the hashtag which I keep on polling, Nikhil EV3 and Nikhil EV4. And you can write a command like forward, reverse, left, right, sound gong. And just an example, GIDS.17, keep GIDS in there, GIDS.17, so that we can actually figure out how many people tweeted at GIDS versus at Java 1. And you guys can control these guys. I poll every 15 seconds because have you guys heard of Twitch Play? So Twitch Play is something where you solve a problem by democracy. You keep on voting for, okay, this is what we want to happen, this is what we want to happen. Okay. Now, if everybody starts tweeting different commands, it's going to be chaotic, right? Sometimes chaos is fun. It becomes chaotic. But what I do is I end up finding the top 2 commands which I get by using one of our API, which is there. And depending on whatever you have tweeted, it will end up doing that. So since nobody's tweeting, or is Steve tweeting? Nope. Oh. Is the internet connection? Yeah. Okay.
Is it also liquid also?
Okay. Let's see. If not, there's one more demo which I want to show you guys before we break. And I think lunch is right after this one, right? So I don't want to keep you back so that you will have a long line. It's on my AR drone. Again, drones are not supposed to be in India, and I did not know this till I was held up in customs, and then I showed them that, hey, this is actually for GIDS, and I'm going to do some robot demos. Sorry, there's some problem with the connection, so the Twitter one is not working, but that's how it ends up, you can tweet to it. And we have videos. I have Steve who can tell that, hey, this actually works. And the drone, so have you guys heard of Stephen Chin? See, everybody has. How many of you have heard of Nikhil Nanivadekar? So Steve actually has a book with the Raspberry Pi on Java, and in that there's this drone exercise, which is chapter 7, and using this drone is so he has pretty much gone through all the steps that you have to do to get the drone working. What I decided was, hey, we'll take it a step further. And Brendan Considine, he works with speech recognition and everything, and he gave me a bit of his code. And what I did was, now I have a drop wizard application, and I can speak here. And if all goes well, it will connect to that AR drone, and I can voice control it. Okay, so let's see. Okay, so this is connected, and again, one of the most important things ever is to have a kill switch. So in my drop wizard application, I have a UI which is going to do stuff. So, hi, hi. Hi. I'm going to disconnect the HDMI cable because I think the audio is getting interrupted. So you guys won't see anything. Okay. Fly off. Land. Land. But yeah, this has left, right, up, down, and crash landing. Yeah. The one quick thing which I want to show is if you guys want to take a video, I'm just going to make it go up and make it go down, so that you guys saw a crash landing, and now you'll see a proper one.
I'm surprised you guys in the front row haven't moved yet. Very.
Yeah, yesterday folks were like, I told them, like, do not try to do not try to stop the drone, just duck, okay? So I have the kill switch, I just hit escape and it will end up coming down. So do not worry, I have your back. Fly off. Fly off. Land. Thank you.